Please go ahead, Dustin.
Okay, great. So let me actually, I think I might have a little more time than I thought. So I've decided to actually go back and give one of the arguments that I didn't give last time. Because I think a similar is going to, a similar concept might come up again later. So let's say, how do we control limits? In condensed sets. Or how to prove that, for example, how to prove that condensed sets has all limits. So suppose we have a collection of objects. We have a limit diagram. Well, we have a diagram. Then each term in the diagram is going to be a kappa condensed set for some kappa. And by enlarging kappa, we can assume kappa is the same for all of the objects in the diagram. So each object in the diagram is a colimit of kappa small condensed sets for some fixed kappa. Put it in some common kappa condensed. Then we want to know that what happens when you take the limit there, what happens, and then when you increase kappa prime. So right. So so if I take the limit over my objects, and then I increase kappa to kappa prime. So this will be my notation for this functor from kappa condensed sets to kappa prime condensed sets for kappa prime bigger than kappa. Then the value on this, well, maybe, no, actually, I want to do it the other way around. I'll try my erasing skills. Excellent, that was very smooth. I'll make it kappa prime and then I'll increase it to kappa. Then the value of this on a t is going to be the colimit of t mapping to, t alpha. So t alpha being kappa prime small of, yeah. Or maybe I should actually just, I'm sorry guys. Let me actually just write the x thing here. I'll write x here and then we'll think about what happens when we take a limit of x's. So x of t alpha. Right. And so the point is going to be, so if we can guarantee that the colimit is cardinality of the diagram filtered, then this functor will commutes with the limit over the diagram. So what does it mean for a colimit to be to be lambda filtered? It means that if you have any lambda small subdiagram, basically it admits a cone. So you can kind of cone it off to a single point. And it's just a general fact about this sort of situation. You might know this in the case of, you might know filtered colimit without the lambda as meaning every finite subdiagram can be coned off. And you might know that filtered colimits always commute with finite limits. But this kind of thing generalizes to higher cardinalities as well. So if you want to commute with countable limits, then it's enough to be what's called Aleph 1 co-filtered diagram. So every countable subset has a cone. All right, so how do we guarantee that? So the key lemma is this. So, well, if let cofinality, well, be the cofinality. Cofinality the cardinal K. So this is the this is the largest cardinal such that if well, such that cofinality kappa indexed sum. Oh no, well, no, sorry, I'm saying it wrong. It's a cardinality which is characterized by the following property. So, oops, did I? Oh no. Oh, I'm still erasing. There we go. Lambda is less than the cofinality of kappa if and only if any lambda indexed sum colimit of kappa small sets is still kappa small.
Limit.
What?
Colimit? Limit?
Colimit.
Okay. Ah,
Yeah.
Sorry. Yeah.
Yeah. Right. Right. So then the claim is that cofinality of kappa can be made arbitrarily large by increasing kappa, I mean. And the second claim is that the category of maps from the category that we were taking our filtered colimit over is cofinality of kappa filtered. So our colimit category that we were considering is cofinality of kappa filtered. So why is claim 1 true? Why can the cofinality of kappa be made arbitrarily large? Well, you can do it using this Beth hierarchy that I talked about earlier. So it turns out, so I told you that for a limit ordinal, the corresponding Beth number is a strong limit cardinal, so we're allowed to use it. And in that case, you can check that the cofinality of that Beth number is the same as the cofinality of the ordinal, where the definition of that means it's the the cardinality of the largest cofinal subset. Okay, and you can make the cofinality of an ordinal as large as you want by taking the successor ordinal of a given cardinal. So let me just write that out. So you can take kappa to be Beth of lambda plus to make lambda less than cofinality of kappa. So there's this plus operation from cardinals to ordinals, or if you take the collection of all ordinals of cardinality less than lambda, then that makes a new ordinal called lambda plus, the successor ordinal, I guess. And yeah, so this, you have to do a little bit of set theory to check that this works, but this is the prescription that will make this true. And then why is this category cofinality of K co-filtered? It's enough to show that a maybe I said this wrong. No, that's right. Right, yeah. Then cofinality of K small limit of kappa small compact Hausdorff spaces is kappa small. Why? Because we give ourselves a diagram like this of maps from T to some T alpha. Then we take the limit over it, and by our claim that's going to be kappa small. It's not necessarily extremely disconnected, but we already know we can surject onto that from extremely disconnected, and that makes a cone for our diagram. So it's not a limit. It's not a limit cone, but it doesn't have to be a limit cone. It only needs to be a cone to satisfy the definition of the colimit diagram being co-filtered. Okay, and how do you show this? For this, it's enough to bound the product. Because the limit will be a subset of the product, and kappa small just means that the underlying set is kappa small. And then you can use this little trick. So, I guess Cantor's diagonalization. So you can bound this guy in terms of the power set. But the product of the power sets is the same as 2 to the sum of the guys here. But now if each of these is smaller than the cofinality, then by definition of cofinality, their sum is still smaller. But that is also less than kappa by the definition of strong limit cardinal.
Sorry,
So,
not 2 to the kappa.
what's that?
Not 2 to the kappa, 2 to the max of the kappa I.
No, but if sorry, if all, I was about to add if kappa I are all kappa small.
You wrote less than 2 to the kappa, and then you wrote less than kappa. So the last inequality is definitely wrong.
Oh, I'm so sorry. Thank you. Yes, thank you. Yes, yeah, less than something less than kappa. Yeah, some I don't know what to call it, lambda strictly less than kappa. Yeah, and then by the definition of strong limit cardinal. That's horrible notation. First of all, I apologize. Maybe I should fix it. Yeah, and then by the definition of strong limit cardinal, this is less than kappa. Thanks, Peter. Right. So, okay, so now let's go back to what we were trying to show. Yeah, so then if we do this change of universe, not universe, but strong limit cardinal, this change of universe functor, it's going to preserve the limit of your diagram, provided your kappa is large enough that its cofinality is bigger than the cardinality of the diagram. And all sufficiently large kappa won't satisfy that. Well, arbitrarily large kappa will satisfy that, and so the limit will stabilize at all sufficiently large kappa. Okay, that's an example of how you reason with the set theoretic technicalities. That this is how you reason that you can ignore the set theoretic technicalities, that you don't leave this world of condensed sets, even with this annoying fact that the generating objects don't form a set, but a class. Okay, so that was a little leftover from the previous lecture. So now let me start with the relation to topological spaces. And I want to actually start by working internally to condensed sets. So, well, first of all, we know that, first, because the topology is subcanonical, so these representable presheaves, these representable presheaves, in this category of compact Hausdorff spaces, these representable presheaves are sheaves for the topology. This implies that these representable objects give a fully faithful embedding of compact Hausdorff spaces into condensed sets. So we certainly have those basic building blocks sitting in there, but we'd like to know what else. Let me start with a remark or a claim. So we can also characterize these compact Hausdorff spaces intrinsically in terms of finiteness properties of condensed sets, ones which actually Peter mentioned in the first lecture. So this is exactly the full subcategory of quasi-compact, quasi-separated condensed sets. So let me give the proof. So what do we have to show? Well, we first have to show that every compact Hausdorff space is both quasi-compact and quasi-separated, and then we have to show the converse. Well, first of all, each object of compact Hausdorff is quasi-compact because of the nature of because of the finitary nature of topology. Well, let me spell that out in words. So in the definition, recall the definition of quasi-compact. It means that if you take an object in a topos is quasi-compact, if whenever you have a disjoint union of other objects mapping to it by an epimorphism, then there's a finite subset of it that still maps to it by an epimorphism. But now, every object in a topos admits an epimorphism from a disjoint union of representables. Because you can just take the disjoint union over all possible sections over all possible open subsets, so to speak, and then make the corresponding map from the representable there. So if you want to find a finite subset for a given disjoint union diagram mapping to your guy, you can actually, it's enough to, what I'm trying to say is that it's enough to check this condition when the objects in the disjoint union are actually themselves members of the defining site. So it's enough to check that for things in the defining site, that if you have an arbitrary disjoint union of things surjectively mapping to your compact Hausdorff space, then some finite subset also surjectively maps. And this essentially is by construction, that we only used finite covering families in the definition of our topology. Right. Now, why are they also quasi-separated? Well, because the definition of quasi-separated was that, right. So that's, yeah. Also, if X is quasi-compact, it admits a surjection. From a compact Hausdorff space. For the same reason, any object can always admits a surjection from a disjoint union of representables, but if it's quasi-compact, then it admits a surjection from a finite disjoint union of representables. But a finite disjoint union of compact Hausdorff spaces is still going to be a compact Hausdorff space. Okay. So now we want to check that a compact Hausdorff space is also quasi-separated. So we're supposed to take we're supposed to check that the fiber product, if we have two maps from quasi-compact guys, then the fiber product is also quasi-compact when this is compact Hausdorff. But if this is surjected onto by a compact Hausdorff space, and this is surjected onto by a compact Hausdorff space, then this fiber product will be surjected onto by the fiber product of the compact Hausdorff spaces. Yeah.
It will be, I mean.
What?
When you check for quasi-separatedness, you don't have to check for maps from arbitrary quasi-compact ones. You can choose your generators. So you can assume that these two guys are already compact Hausdorff ones.
Yeah, that's essentially what I was going to be arguing by hand. Yeah. Should I leave it at that then? Maybe. Yeah. Well, I guess this is an if and only if is the thing I was going to say. Right. So essentially, because the compact Hausdorff spaces are closed under fiber products, you know also that they're going to be quasi-separated. So that means that if you're compact Hausdorff, then you're quasi-compact and quasi-separated. Now, conversely, if you're quasi-compact and quasi-separated, well, we can make a surjection from a compact Hausdorff space. But then the fiber product, y cross xy, is also going to be compact Hausdorff. Oh, sorry. Is also going to be quasi-compact, and therefore we can make a surjection onto it from a compact Hausdorff space Z. And now what does that tell you? That tells you that wait a second. This should all be just formal topos theory stuff. Anyway, this will tell you that X is gotten by it's the quotient of Y by a closed equivalence relation. It's a compact, which means it's a compact Hausdorff space. Right. So the compact Hausdorff spaces are exactly the quasi-compact, quasi-separated condensed sets. So that's nice. That's another good thing about this defining site.
And actually, one thing about this argument here is that you need that the kind of obvious co-equalizer that you take, say, in topological spaces or something, is also the co-equalizer in condensed sets. And that's another point where you really critically use that we have exactly this Grothendieck topology.
Yes, yeah, that's right. Yeah, I mean, that's essentially what that's what this having this Grothendieck topology is forcing. Yeah, something quasi-compact but not quasi-separated. You can take like a compact Hausdorff space. Actually, I can do you even better. I can give you a compact object, which is not quasi-compact. So you can take a equivalence relation on a compact Hausdorff space, which is a relation on a closed relation on a compact Hausdorff space, which such that the equivalence relation generated by it is not closed. And such things show up quite frequently. For example, taking some irrational shift. Yeah, I don't know. It's not too difficult to produce examples. And it'll be a finite colimit of compact Hausdorff spaces in condensed sets, but it'll still be it won't be quasi-separated. It won't be Hausdorff. Okay. All right. So that's the quasi-compact and quasi-separated ones. Now. The quasi-compact things on their own are maybe not so interesting because they include all sorts of non-Hausdorff examples, like actually the thing that I just mentioned. But the quasi-separated ones are worth talking about. So quasi-separated condensed sets. So here the claim is a condensed set. This is basically, you should think of quasi-separated, by the way, as just some fancy way of saying Hausdorff. It's very similar to Hausdorff in the topological context. So a condensed set is quasi-separated if and only if it is a filtered colimit of compact Hausdorff spaces along inclusions, injective maps, which correspond to closed inclusions. Well, I don't have to say closed because a map of compact Hausdorff spaces is always closed. But maybe I'll put it anyway for emphasis. Right. So the proof will be, well, for the backward direction, it's kind of a general topos theoretic fact, which is not.
So in what category is this filtered colimit? Can you take either compact topological spaces or condensed sets?
No, you have to do it in condensed sets. This colimit is taking place in condensed sets. I'll give an example in just a second. All right, so the forward direction is that, well, in a general topos, quasi-separated objects are closed under filtered colimits with injective transition maps. I think that's a general topos fact. In any case,
yes, that's right.
Yeah, if you try to prove it, you'll see that it's not too difficult in any case. You just follow your nose. Okay, and for the forward direction, okay, so let's say X is quasi-separated. What we want to show is that, well, there's a certain sub-object you can write down, which is the filtered colimit. Really, it's a filtered union over all compact Hausdorff. mapping via an inclusion to X. So this is going to be a sub-object of X because, again, by general topo stuff, a filtered union of sub-objects, even, yeah, or an arbitrary union of sub-objects is a filtered colimit of sub-objects is still a sub-object.
It's not ever clear that this is filtered, but you will prove it anyways.
That's correct. Yeah, thank you. It's not a priori clear that we want, this is, you're right. So maybe I should write union, yeah. Yeah, this is filtered and, yeah. Maybe I should be saying this differently, yeah. Yeah, well, we want to show this. Let me put it that way. So how are we going to show this? Right. So the key, it will be the following. If we have any compact Hausdorff space mapping to X, then we can take the image, something you can do in any topos again. So then that's a sub-object. So if this is compact Hausdorff, this implies that this guy is also compact Hausdorff. So the image of a map from a compact Hausdorff space to a quasi-separated condensed set is represented by a compact Hausdorff space as well. Right. So how is this proved? Well, actually, let me recall to you how you define the image in a general topos, essentially. So it's the colimit of k cross x k mapping via the co-equalizer of this diagram here. And this is going to be quasi-compact and quasi-separated because x is quasi-separated and k is quasi-separated. Yeah, the quasi-compact, quasi-separated objects are closed under finite limits. This is something that's not too difficult to show. So it means it's a compact Hausdorff space, and therefore, again, we have this is the quotient of k by a closed equivalence relation. It's a compact Hausdorff space. So we have a tautologically. So let me try again with this this colimit here. So we have tautologically that since the compact Hausdorff spaces are a defining site, this is tautologically the colimit over all compact Hausdorff spaces mapping to X, not necessarily injectively. And then we have the subdiagram in here with compact Hausdorff space mapping injectively to X. And what we just showed was that this diagram here is kind of cofinal in this diagram here, which means that the inclusion map is actually an isomorphism. And then X is this, and it's the same thing as that. So we get what we wanted. Right. And let me make an addendum to this. So if, well, if we have a filtered union, a filtered colimit of compact Hausdorff space along injective maps, and we take their Hom in condensed sets, this is calculated purely formally. So it's the inverse limit over I in I of Hom ki, of the colimit over j and j of Hom ki kj. So in other words, quasi-separated, this is along injective maps, injective transition maps. So quasi-separated condensed sets is the full subcategory of of compact Hausdorff spaces spanned by those with injective transition maps. Right. So these quasi-separated objects, which are kind of the analog of Hausdorff in the world of condensed sets, they're very easy to describe. It's very easy to describe the manner in which they're built out of compact Hausdorff spaces. By the way, these are the same as Valbrook's compactological spaces, which he proposed as a good framework for doing functional analysis, was using compactological vector spaces and so on. So yeah, but I want to make a warning. And a corollary of this is that compactly generated weak Hausdorff topological spaces. I'll remind you what that means in just a second. These sit fully faithfully inside condensed sets via the association, well, X goes to, T goes to continuous maps from T to X. In particular, it is a condensed set. In other words, satisfies this set theoretic technicality when X is a compactly generated weak Hausdorff space. What does this mean? Well, compactly generated weak Hausdorff is the same thing as saying it is the filtered colimit of its compact Hausdorff subspaces. Filtered colimit in top now, Dan, in the category of topological spaces, and any map from a compact Hausdorff space has closed image. So if the topology is formally determined from its compact Hausdorff,
no, that's automatic.
What?
I think the first condition is good enough.
I don't think so. No, I don't think so. No, I don't think so. I mean, you need the.
I think there's a general statement that whenever you take a filtered colimit of compact Hausdorff spaces along inclusions, as you're doing here, then this is always a compactly generated weak Hausdorff space. It's not obvious. So the proof of this is kind of, you have to think about it, but it's true.
Are you sure?
Yes.
Huh. All right. Well, in any case, in practice, it's not too difficult to check the second condition. So maybe I'll leave. So Peter says this is, I don't quite believe it yet, but you know, I'll have to check it out on my own. Not that I don't trust Peter. Right. Yeah, I guess the usual definition of compact generator is, yeah, well, anyway, it doesn't matter. Oh, is it because I said filtered, you're saying?
Maybe.
Yeah, I don't know. Anyway.
I mean, I'm just claiming that this functor that takes any quasi-separated condensed set to a topological space, which is somehow taking this filtered colimit in this case.
Right.
That this always lands in compactly generated weak Hausdorff spaces.
Yeah.
Yeah.
Right.
I was surprised by this too, but it's
okay. So maybe this is not necessary then. Okay. Okay. Yeah, that is a little strange. Okay. Anyway, this implies then that, well, that the associated condensed set. So, sorry, continuous maps from. This is the same thing as the union of overall compact Hausdorff subsets of continuous maps from blank to K. So for any map from a compact Hausdorff, you can factor it through its image. And so you see that it comes from this subset here, which means that the associated condensed set is the union of overall compact Hausdorff subspaces. Maybe I meant to say, yeah, maybe what I was supposed to say is that it's the colimit of its compact Hausdorff subspaces, and then I would need the second condition. But yeah, well, anyway, Yeah, so this is how you describe, so then, yeah. So compactly generated weak Hausdorff spaces, in fact, are inside quasi-separated condensed sets, and they are given as the filtered colimit of their compact Hausdorff subspaces. Now it's time for me to issue a big warning. It's not enough to take any, to take any compact Hausdorff subspaces, filtered unioning to X. You have to use all of them.
Is that a word?
What?
Is that a word? Filtered unioning?
Yeah, let me make it more precise. So let me give an example. Take any sequential space, for example, the unit interval. We can write this as a filtered union of compact Hausdorff spaces. In top, I mean. Of compact Hausdorff spaces isomorphic to the sequence space, n union infinity. Namely, just take, a finite disjoint union of them, say. Sequence space n union infinity. Namely, just take all of the copies of this space that you see sitting inside your 0, 1. Okay? So this is filtered because I said you take finite disjoint unions. So you can take a union of any two such subspaces will still be such a subspace. And I claim that as in the category of topological spaces, this is a filtered colimit diagram. That's just the same thing as saying the topology is sequential. A set is open if and only if its restriction intersection with every sequence plus a limit is open. But this colimit is not preserved by the functor compactly generated weak Hausdorff going into condensed sets. So in condensed sets, the right-hand side is a smaller subset. It's a smaller condensed subset of the closed unit interval 0, 1. So in condensed sets, you're breaking apart some colimits that exist in topological spaces. And one could say, if one were inclined to demagoguery, I don't know, one could say that you didn't want this colimit diagram anyway. It's a bad colimit diagram. For example, it's not good for calculating cohomology. It's kind of by some topological accident that this is a colimit diagram in topological spaces. And it's broken when you pass to associated condensed sets. So the moral of the story is there are a lot more quasi-separated condensed sets than there are compactly generated weak Hausdorff spaces, because you have things like this. Okay. Wow, have I already, so I'm going until, what it was now, 3:45? Yeah,
Yes.
okay.
Yeah.
Yeah. All right. So, what else did I want to say?
Maybe I want to stress it somehow. In condensed sets, you really get the better answer. I mean, in some sense, you wouldn't expect this filtered colimit to be all of 0, 1, right? Doesn't feel like you've built up the whole thing. I don't know.
Yeah, I don't, Scholze, to answer your question, I don't exactly know quite a good characterization of the essential image of compactly generated weak Hausdorff and quasi-separated condensed sets. We'd rather forget, I mean, we can use this to produce good examples of quasi-separated condensed sets, but then we'd rather probably forget about the world of CGWH spaces and just work in quasi-separated condensed sets instead.
Maybe one comment worth making is that if the index set is countable, then there are no problems.
Right. Yeah. Thank you. That's a good remark. Yeah. But yeah. The functor does preserve countable countable unions, countable sequential unions along closed subspaces. Yeah. It also preserves well, it also preserves infinite disjoint unions. So some infinite unions are okay. And it also preserves, for the algebraic topologists in the audience, it also preserves push-outs of compact Hausdorff spaces where one map is an inclusion. Yeah, so things like if you're building up your finite CW complex using, by attaching cells, then that push-out diagram you're used to in topological spaces is still a push-out in condensed sets. So really, it's only a somewhat strange colimits that are not preserved by this functor. All the normal ones that you usually wind up wanting to consider anyway, these countable unions along countable chains, infinite disjoint unions, standard kinds of push-outs, those are all preserved by this functor. Okay, there's maybe one last thing I want to say about the quasi-separated condensed sets, which is that there exists a left adjoint to the inclusion. The quasi-separification. So how do you build it? So you can take your X, and you can write it. You can make again a disjoint union of compact Hausdorff spaces, surjecting onto X, and then there's going to be some. Then X will be the quotient of this by some equivalence relation. Which will be some subset of kappa, disjoint union of kappa I cross kappa J, or it'll really be a subset of, live inside the fiber product, but that in turn lives inside the product here. And we can just take just enlarge by taking the smallest closed equivalence relation generated by it, which is just going to be the closure of the am I saying this right? Yeah, I think I'm saying this right.
Yes.
Yeah. Take the smallest closed equivalence relation generated by it. And then if you do this, it's quite easy to check that it satisfies the universal mapping property required to be the quasi-separification. And therefore, in particular, it's independent of the presentation that you chose and so on. And there's an important fact, which is that this X goes to X quasi-separate preserves finite products. And that is going to imply that it induces analogous functors on condensed abelian groups or condensed rings or any kind of algebraic structure that's described in terms of some number of operations on a given condensed set. So you can always take your, you can always find a maximal Hausdorff quotient, and it's going to behave well with your algebraic structures. Okay. Yeah, so I want to explore just again a little bit some of the distinction between condensed sets and topological spaces. So far I've focused on these kind of Hausdorff phenomena. Was about Hausdorff phenomena. But it's actually important that we have a lot of non-Hausdorff phenomena too. Not important, but it's just completely necessary. So let me give an example. Well, this is a classic thing, I guess. Let's look in condensed abelian groups. And let's look at the Q mapping to R. So Q with the discrete topology, for example. Mapping to R with its usual topology. So these are all, by the way, well, actually, sorry, when I was talking about compactly generated weak Hausdorff spaces, I forgot to mention, I gave you the definition, but I forgot to mention that there are a bunch of more recognizable conditions that imply compactly generated weak Hausdorff, among them sequential. Or locally compact. And maybe that already covers every example of a topological space you usually consider. So, if, for example, the topological space underlying any metric space whatsoever is automatically compactly generated weak Hausdorff. And same with any locally compact topological space. So really, this is a lot of classical examples of topological spaces that you can just transport over into this new context and work with there instead. But the virtue of working in this new context is that you have these good categorical properties, but it does come at a price. So let's look at this map here. If we were doing this in topological abelian groups, this map is both a monomorphism and an epimorphism. So it's a monomorphism, well, because this sits inside of there, but it's an epimorphism because the image is dense. And that implies that if you have a continuous homomorphism here, it's determined by what it does on the rational numbers. But it's certainly not an isomorphism. Not an iso. But when we pass to condensed abelian groups, something has to break here. Something different must happen. Because condensed abelian groups is an abelian category. So in any abelian category, if you have a map which is both a monomorphism and an epimorphism, then it must be an isomorphism. So, well, it's still, I'll say, obviously a monomorphism, because how do you take the associated condensed abelian group? You just say for every compact Hausdorff space or whatever, you look at continuous maps from that to this guy, and that's the value of your condensed set on that. But okay, maps from here to here is always going to sit inside maps from here to here just because this map is injective. So it's still a monomorphism. So we have Q sitting inside R, and it's certainly not an isomorphism because, again, I guess this is discrete and this is non-discrete. So what must be happening is that there's a quotient, which is a highly non-Hausdorff condensed set or condensed abelian group. Non-Hausdorff meaning non-quasi-separated. But we have to have this in there if we want to have an abelian category, which we do. In fact, you can kind of do even worse, so to speak. You can look at R with the discrete topology mapping to R with the usual topology. And again, this will be an injection, and we'll have a corresponding quotient, which is so non-Hausdorff that, in fact, its whole underlying set, so to speak, is 0. So I should have maybe mentioned this close to the beginning, but every condensed set has an underlying set. So underlying set of a condensed set X. It is just the maps from the terminal topological space to, yeah, this is the terminal object in the category, but it's also represented by the point as the compact Hausdorff space, for example. Right. So it's so non-Hausdorff that it has a vanishing underlying abelian group. But for example, we'll be able to see that if you take R divided by R delta and evaluate it on S1, you get something non-zero. And in fact, this kind of, it's basically a closed one forms. Well, it's going to be, it'll be the same as what you would see in a sheaf theoretic perspective. So it's kind of continuous functions with values in R modulo constant functions. Well, in fact, by definition, if you take R minus R delta, how would you calculate this? So a priori, all you know about if you have two condensed sets that you know, and then you perform some operation on them, you want to know what it is. A priori, the only thing you know anything about is what happens on an extremely disconnected compact Hausdorff space. Because those are the things where evaluating on it commutes with everything, as I mentioned before. So this is R of t divided by R delta of t, which is continuous functions from t to R modulo locally constant functions from t to R. Oops. Oh no, what have I done? Excellent. Right. Yeah, so this is probably good to go through as a general discussion. Yeah, because this is the way everything is always going to go. We'll have some construction in the world of condensed sets, and we want to understand it, which basically means we want to understand its values on all, say, compact Hausdorff spaces, or at least all profinite sets. And what we a priori know is only what it does on an extremely disconnected compact Hausdorff space. That's the things for which mapping out commutes with all categorical operations. So here we can just do the calculation. So by definition, you get continuous functions from t to R here. And you'd have to unwind to see that kind of, well, on an extremely disconnected space, the topology is that of finite disjoint unions. So it's basically the same as just calculating the sheafification of the constant sheaf on that topological space, which has a basis of closed and open subsets, and you get the locally constant functions. Right. And if you want to know what happens to a general compact Hausdorff space, you have to resolve it by extremely disconnected ones in one way or another. Oh, sorry. Yeah. So you have to make, depending on what you're interested in, you might have to continue. And then it's actually quite unclear that you're going to be able to do any kinds of calculations so that you can understand what's going on in S1, because this whole process of doing these resolutions is very inexplicit. But Peter is going to give some, present some tricks that we've discovered in the next lecture that actually help you get a handle on this kind of thing. And for example, be able to completely describe what this thing does on S1, even though a priori to figure it out, you have to look at some crazy resolution like this, which doesn't have any geometric meaning. In the end, you still get a geometric result, sort of, so-called sort of like closed one forms. Right. Okay, one last thing I want to mention, which has to do with these set theoretic technicalities. I don't think I'm going to have time to give the argument, so I'll probably just state it as a result, or as a remark. So I said that if for X a general topological space, then this continuous functions to X is a sheaf on compact Hausdorff spaces. When is it condensed? When is it a condensed set? I.e., so this has to do with the set theoretic technicalities. When is it the case that cont X is a small colimit of representables. And the answer is, if and only if the space is satisfies the Kolmogorov axiom T1, meaning all points are closed. So that's kind of interesting that there's this nice characterization. I don't know how important it is. Like, I don't think, I mean, it's important that compactly generated weak Hausdorff spaces do give examples, but I don't know about these general T1 spaces, but it's kind of cute that you can actually completely answer this theoretic question, and it corresponds to a classical separation axiom. You can see the proof in Peter's notes, condensed.pdf, which I think he linked in the chat earlier. Right, so I guess I'll call it quits a little early today, or maybe if people have questions, I can try to answer them. But next time we meet, Peter's going to be doing some serious calculations with these condensed abelian groups here.
Thank you, Dustin. So, do you want to say something?
Questions? Dustin, ask the questions.
Can I ask a question? Hey, Dustin.
Yeah.
So when you set it up, you use what is it? Strong limit cardinals.
Yeah.
Could you use regular cardinals instead? Let kappa. No, you need the strong limit.
I mean, if you tried to cut off at a regular cardinal, there would be a difference between these three defining sites.
I see.
And that's not good. It means the limiting theory would behave quite differently from the limit theory of condensed sets. That said, from the perspective of the sheaves on profinite sets, regular cardinals are also a reasonable cutoff, but you should instead use, maybe it's equivalent, but you should, a priori, you should use the lambda, for the regular cardinal lambda, you should use the lambda co-compact objects. It might be the same as lambda, I forget what the relation is with smallness condition on the underlying set. It might even be more or less the same. No, anyway, I don't know, it's the same, maybe the same as a smallness condition on the collection of open subsets or something like that. Which is different when you don't have a strong limit cardinal. Yeah, I didn't mention it, but there's I said so condensed, yeah, there's three characterizations of condensed sets in terms of sheaves on compact Hausdorff spaces. Either it's the, or on the other defining sites, either it's just a small colimit of representables, or in this extremely disconnected picture, it's a sifted colimit of representables. And then you don't even need the sheaf condition if you say that. And in the profinite set condition, it's the condition that the functor be an accessible functor. So it commutes with sufficiently co-filtered limits, or sends those to co-limits rather, since it's a contravariant functor. Yeah, anyway, and then that second context, it's regular cardinals that are the most natural. In the profinite set context, with that specific condition, it's regular cardinals that are the most natural. But I think in general, you probably want to choose strong limit cardinals as your cutoff. Yeah.
It's anyways a cofinality that appears there.
What's that?
It's a cofinality that needs to be regular. And I think the cofinality is always regular anyways.
Cofinality is always regular, yes, but
and in this question about this accessibility, it's somehow what's relevant to see how filtered or co-filtered this index category is.
Right. Yeah.
And that's the cofinality of kappa that's relevant there. So.
Right. Mm-hmm.
By the way, for this last thing that you just mentioned, that is characterized by the space being T1, this came as a complete surprise when I started writing up the notes. So I was imagining that all topological spaces should give condensed sets, and then I tried to write up a proof and realized that this doesn't work at all.
Huh. Yeah, it's an interesting fact. I just don't quite know. Yeah, don't quite know how to situate it. Yeah. Anyway, thank you guys for listening. I guess I'm officially out of time now, so I'll say see you tomorrow.